Hi, I'm Michael Esposito, and I'm here to talk to you about the automated transport vehicle. Now, I'm primarily focusing on my specific portion, the computer science portion, but this project would not have been possible without the help of John Buckles and Cassidy Schmitz from the Mechanical Engineering Department, Shrevi Tiramala from the Biomedical Engineering Department, and Camelia Zafar from the Systems Engineering Department. There may have been a time when either you or someone you know had a laptop, 3 notebooks, all of their pencils, all of their chargers, and they couldn't carry them from home or work or to get to school or wherever they had to go that day. It may have been due to injury, there were too many items to fit in the backpack, or the items could have simply been too heavy to carry. Now, wouldn't it be really nice if there was someone or something to help you get all of your things from point A to point B? And that is where a personal transport vehicle could help. Unfortunately, personal transport vehicles are still relatively uncommon in today's society, and this is due to numerous obstacles that they face both in daily usage and construction. First obstacle are curbs. Curbs are relatively easy for humans to recognize and find a way around. Ducks have a hard time recognizing and finding a way over a curb, as would a robotic device. The same applies for walls. Walls are pretty easy for humans to both see and find a way around, but slightly harder for robots to do the same. The next subject is the subject of battery life. Personal transport vehicles should be able to carry heavy cargo. Heavy cargo requires bigger motors, and bigger motors require bigger batteries. Therefore, it's hard but imperative to strike a good balance between battery life and cargo carrying capacity. It's also important that personal transport vehicles work in as many environments as possible. Customers may live in an environment with a lot of grass, a lot of dirt, a lot of trees, or they may live in an urban environment with a lot of roads, or cars, or other people. Personal transport vehicles should work in rural and urban environments, and any environment in between. While working on this project, our team divided it into 3 main components, and these components are the robot chassis, the cargo enclosure, and last but not least, the tracking and control mechanism, which is what I've been working on for the past couple of months. I've divided user tracking into 3 main subcomponents, the first of which is identifying users and separating users from any background data like you can see over here. The next task is isolating the target user and picking one person to follow through the course of ATV operation. And the last challenge is actually following this target user and calculating motor controls and then sending these controls to the respective motors. In order to accomplish these tasks, the ATV gathers and processes various sources of information. The first information source is joint data. When it finds a person, it gathers 5 different joints to classify users with. The first joint is the head. The next ones are the shoulders, a midsection joint, and a center of mass joint. Using each joint in their respective positions in space, it then calculates shoulder width and midsection height. But it also takes these XYZ positions and stores them in a tiny buffer, and that way it can recall the previous location of the target user. It also assigns any person it sees a user ID starting at 0 and incrementing by 1 after that. Here you can see the initialization phase which occurs once the user stands in front of the camera. This is what the camera looks at when it sees a person. It finds the head, the midsection joint, both shoulders, and hand points, which we didn't use because they aren't always visible during operation. And with that, here we start. First, the user steps in front, and the ATV learns about the target that is attempting to follow. After 100 frames, it has an estimation of torso height and shoulder width. And here it shows the direction that the person is in and that it should be moving towards. Here it's going to the left, going forward, going to the right. Now get to stop, we don't want to run over the user. Now they're far away again, and now a second person enters the screen, but you can still see it's following me because it knows to go straight. And now I am not visible, so question mark, and it spits out right here, target user TU not found. And now I step off screen, it still can't find me, However, this is the user permanence that we have given the program. It's able to recognize the target user again and then follow them. There's the fun part. Now, how does it all work? There are a bunch of cases the ATV needs to be able to overcome in order to work correctly. The first and simplest case is when there is one user, one person in the field of view of the camera, and this person is the target user, in which case it is able to pull a center of mass point and use this data to calculate movement controls and send those controls to the motors. In some cases, though, there may be some confusion about who or where the target user is, and these cases may occur when the user disappears from the field of view or there are multiple users in the field of view. And one such methodology for getting over this confusion is outlined over here. This is the frame of what the camera sees, and it's divided into 4 regions. Now we say there's the target user in frame 1, but they've disappeared. In a successive frame, if the HTV sees a person in the same region, region 0, 1, 2, 3, there's a good chance that this person is the target user, the person that the robot should follow. So it will consider them for target user for classification. However, if the next person it sees is on the other side of the image, very far away in a different region from where we last saw the target user, there's a very low chance that this person is the target user and they won't be considered for classification. Classification of the target user is done by these confidence values, which start high and drop off quickly. They range from 100, being a high chance that the person in screen is the target user, and 0 meaning a low chance that this person is the target user. And these confidence values are created from the user quantifiers mentioned previously, the last known location and the joints, and then combined into a single confidence value which was generated using experimental data. And this confidence value is utilized when the ATV loses track of a target user. If it can't find the target user it's looking for, it will look and give every person in the frame a single confidence value, and if there is a person with a confidence value, with a high enough confidence value over a certain threshold, it will then follow this person instead because there's good reason to believe that this is the target user. It's not a different person, it's a person with a different user ID. Some helpful tech that I've used to create this project. Here we have the upboard. It looks like a Raspberry Pi, however it's much more powerful. It's running a fully fledged Windows 10 operating system which gathers all the informational data, processes it, and then relays controls to an onboard Arduino Mega, which controls all of that motor output to the 6 motors. The eyes of the system is this Intel RealSense R200 over here, which is capable of producing an RGB stream and a depth stream using stereoscopic infrared cameras. These streams are processed using Visual Studio and Visual C++ with the help of the Intel RealSense SDK, which has been amazing. I highly recommend it because it has allowed me to abstract a lot of the raw image processing and instead focus on a lot of the underlying algorithms. Here's a video of the robot in its current state in the upcoming days. Our team hopes to have a moving, functional robot. So it's the end of this presentation. Hope you enjoyed it. Thanks for watching.